Hi, I'm Sara Sabour, and this talk is on our work called RobustNerf. As we know, NeRF is great at multi-view 3D reconstruction from a sparse set of 2D images. So given a set of images, methods like NeRF 360 can perfectly render the scene from all new viewpoints. But if you're given bad images, you get bad results. Right now, if you have transient objects, such as this randomly placed pink balloon, the rendering will be crowded with shadowy clouds and floater artifacts. As a solution to clean up the rendering and ignore the transient objects and distractors, we propose RobustNerf. Let me show you the two side by side. We approach this problem via the lens of robust optimization. RobustNerf optimizes the NeRF model under a spatially curated robust loss. Our poster is on Thursday, and we look forward to talk to you. Now, let me do a deeper dive and explain some of the details. NeRF training tries to find a 3D world that explains the images up to an IID Gaussian noise. Therefore, if the noise is structured like a transient object, it has to fabricate a weird anomalous 3D world. In particular, the L2 reconstruction loss is sensitive to outliers like a transient object or a shadow cast by the person capturing the scene. So the obvious solution is to use a robust loss which can model distractors as optimization outliers. A robust loss replaces the L2 reconstruction loss with a robust kernel. The question is which kernel to use. We already saw the results of Charbonnier loss with NeRF 360, which wasn't ideal. We can try other robust losses, but it's not as simple as it looks. With a more liberal loss, you have good details, but you will get some floaters still. With a more conservative kernel, you can get rid of the floaters, but you will also lose details. The underlying assumption behind robust estimators is that outlier pixels are independent processes, but it doesn't hold for transient objects such as this balloon. So we design a specific robust loss for NeRF with the spatial consistency of objects in mind. Our formulation is based on two insights. First, we know that the outlier objects are spatially consistent, and second, we know that hard masking the transients would result in a perfect optimization. Therefore, we try to simulate having an oracle segmentation S by using iteratively reweighted least squares, or IRLS. In IRLS, the kernel function changes based on the residuals at the previous training iteration. Therefore, as soon as the residuals start to get good, the outliers will pop out, similar to having an oracle segmentation. In order to design the kernel weights, we first filter the residuals in the current mini-batch based on the median of the residuals in the previous iteration. Then, relying on the spatial consistency of the outlier objects, we regularize the weight mask by diffusing the residual mask. And then, we boost the spatial consistency by filtering each small patch, only if the surrounding neighborhood of it is already filtered. Let's take a look at how the kernel adapts for this example where there are 3 transient objects present between training view and ground truth. During training, we can see that at the start, the residuals are high and the weights are overeager, and therefore remove some portions of the scene as well as the outliers. But after few iterations, the weight masks get better. And at around 10% training, the weights fairly closely follow the silhouette of the outlier objects. We evaluate our method on several data sets containing single or dozens of transient objects. Our results show significant improvements in the clarity of the scenes, both quantitatively and qualitatively, on almost all of them. We compare against MIPNERF 360 here with different losses such as L2, L1, and the original Charbonnier loss, as well as D2NeRF, which is a competing state-of-the-art model designed for a similar task. Here we can see the renderings of RobustNerf on the right, alongside the rep map compared to MIPNERF 360 on the left. RobustNerf is only a simple change in the loss function and therefore easily adaptable for many underlying NeRF models. For our experiments, we replaced the MIPNERF 360's loss function in their codebase. We also test our method on more challenging datasets consisting transparent objects, glossy and metallic objects, and objects with mirrored surfaces. It is of considered note that our robust loss does not remove the view-dependent parts of the scene. We also experiment with datasets provided by D2NeRF, which mainly consists of shadow as a distractor. Shadow is challenging since the hues are close. In all cases, RobustNerf is capable at removing all of the artifacts while preserving the quality of images. Let's take a look at the video of the renderings between D2NeRF and RobustNerf on D2NeRF's peak dataset. As you can see, there are slight artifacts appearing at seconds 1 and 6 for D2NeRF, while RobustNerf rendering is clean. Currently, one of the main limitations of RobustNerf is its statistical inefficiency. Throwing away roughly 40% of losses at each iteration results in more training iterations required, and if applied to clean datasets without distractors, it will lower the PSNR of the renderings slightly. We note that one can mediate this by changing the threshold and hyperparameter tuning. The other two limitations are call map and mirrored surfaces. Call map is a known failure point for many NeRF models. Since we rely on call map for camera calibration, its failure due to crowded scenes will hinder training our NeRF models as well. Another challenge currently is handling transients through a mirrored surface, and our method replaces the mirror with blank fixed color rather than true mirrors. Overall, applying RobustNerf is a simple loss change which gives much cleaner results compared to the base NeRF models such as MIPNERF 360. Please visit our website or drop by our poster on Thursday afternoon for more discussion. Thank you.